Well, I hope you enjoyed learning all about tangents to circles. I think they're kind of interesting. They're kind of fun, but different. Um, we're looking at another way that a line or a line segment can intersect or interact with a circle today. And that's called a chord. But as you see on the screen here, it's not that kind of chord. By that kind of chord, I mean this. How about this? That's the musical kind of chord. I know it's going to probably be crushing. We're not actually going to learn about musical chords today. What we are, though, going to look at is a line that intersects the circle in a very special way. If you look at your notes, you're going to see a drawing that looks something like this. Just 1 second here. It's a little bit like this. And I'm going to redraw this drawing here on the whiteboard so that we can talk about these three different types of line: a chord, a tangent, and something called a secant, which we won't be dealing with today, but is it's a topic for a later course. So the first thing we did is we saw what a tangent looked like, and it looked generally like this: a line that kind of passes by and touches a circle, but only in one place. A chord is quite a bit different from that. A chord actually is a segment. Let me just put some names here. This is tangent. This is a chord. And we can define it as a segment that lives only inside a circle, and its two endpoints are on the outside of the circle. Not to be confused, and I apologize if this is confusing, but not to be confused with this kind of shape, which we call secant. And it might not look much different to you, but a secant is a full line, and a chord is just a line segment. When you all get to calculus, you will be very interested in tangent lines and secant lines, not so much chords. You'll treat a chord as a part of a secant line, as if we could actually put endpoints here. And you can see that the segment here would be considered a chord, but the line itself is considered a secant. So what I want to do is just walk you through a whole bunch of theorems today. And it's going to seem probably a little bit daunting at first, but don't panic. I'm going to walk you through them. I'm going to show you what they all are. You probably won't get a chance to really appreciate what this is all about until you start doing problems. But on the screen, what you should see is our third theorem of this unit that says that if you have two congruent chords, and I'll draw this up for you again and kind of recreate it, but if two chords are congruent, then the central angles that form them are also congruent. So let me put that up on the whiteboard. I think sometimes if you see it drawn out, it makes a little bit more sense. So here's a circle here. Actually, I'm going to see if I can move this up. Okay. And I'm interested in two chords that are congruent. So I'm going to try to draw that chord there. I'd love to change the color. See if I can do that. I can't do that. And then I'll draw this another chord over here. And we'll just say, for the sake of argument here, that these are congruent. Okay. So the question then is, well, how are these chords produced? Obviously, there has to be a line segment drawn from the center. I'll put a big dot here to represent the center. And there is an angle here that we'll call X. That is this angle that produces not only this chord, but also, curiously enough, this arc. And remember from before that this central angle here has the same measure as this arc out here. So if I happen to have two central angles, and these are not intended to be what they appear to be, and that is vertical angles, but they're certainly going to be congruent. What this first theorem tells us is that if these two chords, and I'll draw this and I'll take this off in just a second, but if that and that are congruent, then that and that are congruent. Okay, so if you have two chords anywhere around the circle and you know they're congruent, then the angles that formed those chords have to also be congruent. So this is theorem, we'll call it number 3 for now. But I want you to notice that also the converse holds too. What does the converse look like? Well, the converse will say, and again, have your notes out, have your theorems out, look at this again. I'm just reading off my theorem sheet here. So the first one says if two chords are congruent. The converse will say if the central angle that forms two chords are congruent, that is, if these are congruent, oops, if those are congruent, then the chords are also congruent. So we now know that these central angles, if they're congruent, they're going to create congruent chords and congruent arcs, and we're starting to see a relationship maybe between angles, chords, and arcs. But to make sure that the relationship it completes the entire cycle, I want to move on and look at the next theorem, which I will share over here with you. I will go over to this one. Nope. We'll go here and let's think about this. This one now says we're going to connect, so we've connected central angles to arcs, central angles to chords, chords to central angles. This one's going to connect arcs to chords. So don't get hung up on this. It just says that if two chords are congruent, the arcs are congruent. If the arcs are congruent, the chords are congruent. So let me draw that picture for you again. Again, if this is feeling like it's all too confusing, then I would say you're maybe thinking too hard about it. And I'll explain what I mean in just a second here. So let me get this circle out here. What this is saying is the following. If I have two arcs that look like that, and those arcs happen to be congruent, then I can conclude that also congruent are, did I say arc? Let me back up. If I have two chords that are congruent, then I know that the arcs produced by those chords are also congruent. So arcs and chords. That's the theme behind theorem number 4. So if we go back again, remember, this one has angles and chords. And this one now has arcs and chords. And we have the converse that goes here as well. So let me take you back to the theorem sheet so you can see this once again. So again, if we have two arcs that are congruent, the chords are congruent. If the chords are congruent, the arcs are congruent. So I think that completes the entire cycle. We can get from angles to chords, chords to arcs, arcs to angles, angles back to chords, and so on. So what we now get as a result is this little statement, which is, I think, kind of worth just sort of summarizing the collection of the work we've done in one statement. Within a circle, and this also works if you have two circles that are, you know, separate from each other, but they're congruent. Anytime you have congruent central angles, you have congruent chords. Anytime you have congruent chords, you have congruent arcs. Anytime you have congruent arcs, you have congruent central angles. So you can go any direction. Angle, chord, arc, arc, chord, angle. And so what we're going to do is we'll have a chance when we do our assignment is you're going to get a chance to see all this in action. And that's where it gets really, I don't know if confusing is the word, it gets more complicated. And so I'm going to try to take you through at least one example from the homework today so that you kind of see how it all feels. Okay, so for right now, we're just playing with the theorems. We're going to get to the practical application in just a second. We have two more theorems I want to cover. This one is going to be, I'll call number 5. And there's nothing magical about that number. It's just the 5th one we talked about. And not surprisingly, I'm going to draw a circle again. Let me go back to the theorem sheet and let's see what this looks like in words, and then I'll walk you through it. So theorem 5 says if two chords are equidistant from the center. So I want you to look really carefully at that drawing. I'll try to replicate it. We've got these two chords that are just kind of there. We don't really know how they're connected to the center, except that the distance from, say, A to F and A to E is relevant here, and those two distances are equal. So that means if I take a chord and move it up and down within my circle, I'll show you that in just a second. If I get them to the point where the two chords are equidistant from the center, then they're congruent. And similarly, if they're congruent, they're equidistant from the center. So let me go ahead and draw this out, and I'm gonna walk through this one a little bit more slowly than the last ones because I think this is potentially a little bit tricky. So I want to draw two chords. I mean, ultimately, I want them to be congruent here. But here's the thing I was going to show you. I'm going to put the center right here. So I'm interested in this distance right here. Okay, and I don't know if you remember when we talked about drawing distances from a point to a line, it's always the length of the line that's perpendicular to the other line. So that's why I'm kind of eyeballing it there. But my point here is to show you that this chord, and I get that length is weird, but I can move this lots of different places. I can move it up here, and it's that long. I can move it down here, and of course it's going to be much shorter. But I can move it, and it sort of grows as it gets closer and closer or farther and farther from the center. So if I put it here, what I'm saying, come on now. What I'm saying is that I have a chord, actually I have two chords that are equidistant from the center. So I've moved them to the point where they are exactly the same distance from the center, and that makes these chords equidistant, or congruent as well. And then similarly, if let me just try this real quick. If I had this circle here and I draw these two chords, I got one here, one there. If I happen to know that they're both congruent, then that tells me something about how far they are from the center. It means that this distance and this distance also have to be equal. So that's the original statement, and the converse part of that. Let me show you a little preview of what's going to happen from this. So this is where I find it kind of interesting. What happens when we do this is that, well, we're going to be based on this idea of a perpendicular line, right? Of this line drawn from the center of the chord is perpendicular to the chord. And so now if I were to draw this, do you notice I have a right triangle? And the hypotenuse of the right triangle is just the radius. So we get some interesting problems here that involve the radius and or ultimately the diameter of the circle. Don't think I'm trying to draw a diameter there. It doesn't matter if they're in a straight line or not. But most importantly, we have a right triangle. So you now have Pythagorean theorem type problems for these right triangles. That becomes, we'll say, interesting. You can call it complicated. I'll call it interesting. We'll agree to change our terms on that. Okay, one more. What I want to do is go back to the theorems. And this is now our last theorem. Let me read it for you. I will then show you the drawing, and we'll just talk through it. So let's talk about this. Actually, oh, I forgot. There's two parts of this one, so actually there's two more. Thanks. All right, number 6. If a diameter is perpendicular to a chord, let's think about this. What do we know about a diameter? First of all, it goes through the center. We know that each half of the diameter is a radius. So we're looking at radii here. And a radius inevitably is going to cut through a number of possible chords, depending on how you draw them. If the radius, diameter, is perpendicular to the chord, though, so if that's focused on this sort of orangish right angle right there, if that is the case, then this diameter not only bisects the chord, but it also bisects the arc that the chord produces. Whoa. So let me back up. If the diameter is perpendicular to a chord, what does it do? Well, it splits the chord in half, for one thing. It bisects it, but also bisects the arc. Now, look at this one, and then tell me if you think this is a converse. The perpendicular bisector of a chord contains the center of the circle. I think that's a converse. It's not really stated that way in your book, but I think it's a converse. So let's go back up here. We have, if a diameter is perpendicular to a chord, then it bisects the chord. This now says, if we have a line that is perpendicular to a chord and is a bisector, then it's a diameter. Why is it a diameter? Because only the diameter contains the center of the circle. So I think there's a little bit of an issue about where perpendicular falls and where bisector falls, but basically I think that is a converse problem. So I want to draw it up real quick, because then I have one problem that we're going to do together to practice this, and then I'm going to show you a bunch of problems from your homework today. I'm going to do some of your homework. That's fun. So we're going to call this theorems 6 and 7. I'll draw a circle here. I'll put a center right there. And here's the idea. We have a diameter that passes through the center. That's all we know. That's the only way we know it's a diameter that passes through the center. And now I can draw a bunch of random chords, right? That's a chord. But that chord's not perpendicular to this diameter. So I need to get to the point where this chord is perpendicular to the diameter. I'm going to put it there as a right angle there. So this is that case. Only when you've got a diameter that's perpendicular to a chord is this going to happen. And what is this that's going to happen? Well, we have bisected the chord. And we've also bisected the arc that's associated with that chord. I know we talked earlier today about the central angle and the chord and the arc as well. That's not really what we're getting at right here. But what the theorems here say is, if the blue line is perpendicular to the red line, then it bisects the red line and the arc. And then theorem 7, I'll go back and show you this. Theorem 7 tells us, all right, well, if you have a chord, then it's going to have a perpendicular bisector somewhere. Let me show you this real quick. Like if I do a chord here, then regardless then it has a perpendicular bisector. Okay, I'm not saying it's the blue line, but it has a perpendicular bisector. What the theorem says is that perpendicular bisector, by definition, goes through the center. I mean, it becomes a diameter, but it goes through the center. Okay. So let me put up for you a a little practice problem to try here. And then we'll look at some ones in the book. So you have all this. I'd like you to get to this practice problem right there. And I'll let you pull it up. It's in the notes that I handed out to you. I have it right here. So I'm going to switch back to the whiteboard, and I'll draw this up, and then we'll go through all this and see how it works. Don't worry, I got you. There we go. Okay, big old circle, and we're going to have the diameter goes right through the middle, and I'm going to try to mark this center with a dot to make sure that we have a center clearly marked. I'm going to draw a, ooh, I don't think I want to do that. I'm going to draw a chord, but it's got to be set up. It's a little bit off, so let me move this over now. I just want the chord to be about the way it's drawn in the picture, and to make sure that it's perpendicular. So we have a couple of things here. We have a side layer length of this segment, which is 2y plus 1, and then y plus 4. I hope you're following along in the notes packet I gave you. We also have 5x minus 18 degrees and 3x minus 4 degrees. So what this is getting at is probably not a huge surprise here. These two have to be equal. The diameter that's perpendicular to a chord has bisected the chord. So y plus 4 is going to equal 2y plus 1. Remember how to do this? Subtract y. So we get 4 equals y plus 1. You can probably figure out that y is 3, but we'll take away 1, 3. So y plus 4 makes 7 here. 6 plus 1 makes 7, and those check out. But also, the arcs, this big arc, this one right here, it was bisected as well. So 3x minus 4 has to equal 5x minus 18. Add 18. Kind of bummed we did all this work to get all your algebra skills up to ready to go, and then we don't get to use the algebra skills on that test. I'm sure you're not too terribly sad, but it was going to be a great moment for all of us. Minus 3x, and we get 14 equals 2x by 2, x equals 7. And again, we don't just blindly say x equals 7. I'm going to plug in 7 here, and 3 times 7 is 21, minus 4 is 17. 5 times 7 is 35, minus 18 is 17. So I feel pretty good about the fact that I found the values of x and y, but also that they checked out. Okay, I'm going to give you a second if you want to pause this recording. I want to get your book out, and we're going to look at page 441. So let me jump ahead here. I'm going to look at page 441. Basically, 5 through 10. It's one problem, one circle, but a whole lot of questions. So I think this is time well spent. So you know, in another time, I might have not done all these problems for you, but yeah, I'm kind of a good guy, and maybe this will pay off for some of us down the road. So I'm drawing this. I'm looking on page 441, just trying to redraw this circle. So give me just a second to get all the pieces up here. I'm going to need one chord that goes there, one chord that goes here. I want to make sure that they're both perpendicular. We have a marking of 2 right there. Oh, and arc AB is 43 degrees. So let's put this. So this is A, B, C, G, P, F, H, D, N, E. Okay, so let me write down what they're asking for. 5 is asking for DH. Can you remember, sorry, not DH, it's DF. Remember when we first started this year, there was always some confusion about do you put the bar over the top or not? And I want to remind you that when we're talking about the length of a segment, we don't put the bar over the top. We just write the segment. If we're talking about the actual line segment, then we would put a bar. The measure of arc ABC, so you can see where that would go. 7 is FH. 8 is the measure of arc DE. 9 is AC. And 10 is the measure of arc DF. Oof. That's a lot. But maybe it's not so bad. So what do we have here? Well, I certainly see 2 chords, but I don't know if they're congruent. So I don't know anything about their arcs necessarily. I don't really have any central angles here, but I do have a diameter. Okay, it's a radius, but a diameter that is perpendicular to a chord. Right, I'll take this off just a second. It's right here and right there. So going back to my theorems, I look back and I say, well, if the diameter is perpendicular to a chord, then it bisects the chord. So that tells me that if this is 2, that's 2. I don't see AG on here anywhere, but I do see AC, which is going to have to equal 4. So I think I'm going to be able to do number 9 first. You'll notice I'm not doing this necessarily from the perspective of do 5, then 6, then 7, then 8. I started with the problem, and now I'm just sort of working through what I know. Okay. Oh, look, AC equals DF. See that? That's given in the problem. So if AC equals DF, I know that DF also equals 4. AC equals 4, DF equals 4. But wait a minute. Wait just a second. If they're congruent, then that means that the the chords are equidistant from the center. Not terribly sure that helps us, but it was kind of cool to put those on there. Oh, FH we can do though. Look, if FD is 4, then FH has to be 2. And it's not surprising because, well, it has to be 2 because PE is perpendicular to the chord, and it is a diameter. It's a radius, but it passes through the center. And so it has to bisect FD. So I know that this equals this, equals this, equals this. But here's the thing I also know. I know that not only are chords bisected by a diameter, but also the arc. So if this is 43, this is 43 degrees. I don't see arc BC on here, but ABC I'm going to write as 86 degrees because I got 43 and 43. And now I remember something else. I remember that when I have congruent chords, I also have congruent arcs. So this arc right here, which should be DF, is going to be 86 degrees. This is also 86. Congruent chords, cut off congruent arcs. And then arc DE is just this part right here. And again, that represents exactly half of the larger arc. And I know that arc is cut in half because I have a line coming from the center, would be the diameter or the radius, that's perpendicular to the chord. It bisects both the chord and its arc. So DE is going to be 43 degrees. Now here's what I think I see here. And I'm going to be kind of joking about this, but sort of not joking about this. I think you could look at this problem and you could say, oh, AG is 2 because it looks like it. It looks like it's got to equal GC. Then it looks like F and D are the same as A and C. They look a lot like. This, guys, is not the time to use it looks like it. We just got, what, 5 new theorems and converses today? Those are the theorems I want you to be able to use. And what's interesting about this to me is that there's not a whole lot really explained in here in the review. If you look in the review on 441, there's only a couple of concepts in there, but then there's all these theorems that we covered in the book. So this could be a little bit confusing. I've watched some of you throughout the year, and I know that, you know, you kind of copy all the circles down, you got the chords and all that, and then you kind of get to the problems, you're like, yeah, I don't know how to do any of this. So I hope you have your notes, you have your theorems, you have this example, and I'll put these slides up as well. You have this video you can take a look at, and you got me. I'm right here, and you can just call me up or text me anytime and say, hey, how do you do number 18 on that page? And I'll let you know. So page 441, you've got the assignment on your sheet. I don't have the assignment in front of me, but I know it starts with 5 through 10, and I just did those for you. So good working. I'm looking at my schedule. The next day that we should, you can expect a video is going to be Friday, April 3rd, which would have been the Friday of a half day, would have been going into spring break. That's crazy, huh? Seems like a long time ago. Anyway, so Friday, you can expect another video up there. For now, see you later.